All right, let's dive right into this explainer. We're going to break down the absolutely brilliant engineering that keeps thousands of tons of metal suspended in the sky every single day. It's pretty easy to take air travel for granted, but the machines strapped to modern airliners are absolute marvels of thermodynamics. So let's demystify exactly how they work. Think about what happens when you blow up a simple party balloon and just let it go. It zips crazily across the room, right? Well, believe it or not, a 300-ton modern airliner actually relies on that exact same aerodynamic reaction force. Sure, the internal technology is infinitely more complex, but the underlying physics are identical. So here's our roadmap for today. First, we'll look at the physics of thrust, then we'll go inside the engine core. After that, the turbofan revolution, followed by 3 shafts of power, and finally, the physical limits of fan size. All right, section 1, the physics of thrust and how we actually get moving forward. Just like letting the air out of our party balloon, generating thrust is entirely about creating a really high-speed exhaust jet at the tail. Sir Isaac Newton actually hit the nail on the head centuries ago with his third law of motion. For every action, there's an equal and opposite reaction. The faster the jet blasts out the back, the greater the force pushing the aircraft forward. So the crucial point here is that to get that massive forward reaction, we have to master the art of heating and expanding air to extreme velocities. We bring in ambient air, heat it up so it expands tremendously, and then force that expanding air out through a narrowing exhaust case. The result? A massive spike in jet velocity. But as you can imagine, maintaining this kind of highly pressurized continuous explosion takes some serious heavy-duty hardware. Which brings us to section 2, inside the engine core, specifically the gas generator. Now, what's really fascinating here is the brilliant sequential dependency, a cycle often jokingly called suck, squeeze, bang, blow in the aviation world. First, the compressor blades squeeze incoming air to a highly volatile pressure. Then, in the combustion chamber, atomized fuel is continuously burned. But here's the absolute genius part. That high-energy expanding exhaust actually spins a turbine on its way out, and that turbine drives the compressor at the front. The engine is literally powering itself. Because of this thermodynamic reality, you can't just burn fuel in the open air to get thrust. Burning fuel in a high-pressure environment is absolutely essential if you want to extract a surplus of energy. Because we heat the air after it's been compressed, it expands so aggressively that it has more than enough energy to spin that turbine and still leaves a massive amount of surplus energy to shoot out the back and push the plane forward. Let's move on to section 3, the turbofan revolution and the magic of bypass air. Before we dive into modern designs, you need to know a key industry term, a spool. This is a complete rotor assembly. It's the compressor, the turbine, and the shaft connecting them. Engineers pretty quickly realized that one spool just wasn't going to cut it. So modern engines use multiple concentric spools nested inside each other, kind of like Russian dolls, allowing different parts of the engine to spin at totally different speeds. And here is where the real revolution happens. Early turbojets forced all the incoming air directly through that fiery core, which created a single, extremely high-speed and frankly, deafeningly noisy exhaust jet. But enter the turbofan. By placing a massive fan at the front, we can bypass a huge amount of cold air completely around the core. Mixing that cold bypassed air with the hot core exhaust keeps the overall outlet velocity within a certain limit. This beautifully solves the noise problem of older turbojets while also massively saving fuel. So the takeaway here is that increasing this specific ratio, the bypass ratio, is basically the holy grail of modern engine efficiency. If you have a ratio of 8:1, that means 8 times as much air flows around the core as goes directly through it. This lowers the overall exhaust speed, which wildly improves propulsive efficiency. But to do this, you need a massive intake fan. That brings us to section 4, 3 shafts of power, and the Rolls-Royce architecture. So how do we turn those massive fans? Well, this brilliantly illustrates the legendary Rolls-Royce Trent family. Evolving from the RB211 back in the 1980s, the Trent uses a highly unique architecture to push bypass ratios and produce absolutely incredible thrust ratings. We're talking up to 97,000 pounds of thrust for some of these massive wide-body aircraft. Now, while most turbofan manufacturers use a 2-shaft design, Rolls-Royce went with 3. In a 2-shaft engine, the giant fan at the front and the low-pressure compressor share 1 shaft.
But because a giant fan has to spin relatively slowly, otherwise its blade tips would literally break the sound barrier, the compressor behind it is forced to spin slowly too, reducing its efficiency. By separating the fan from the intermediate pressure compressor, this three-spool design means the internal core can spin at its optimal, highly compressed speed, while the massive fan spins at its own safe, much slower speed. To give you an idea of the extreme forces at play here, the high-pressure compressor and turbine inside the core of a Trent engine can rotate at a mind-boggling 13,500 revolutions per minute. Because it has its own dedicated shaft, it's not bogged down by the slower speeds required by the huge fan at the front. Because each section of the engine gets to run closer to its perfect aerodynamic speed, the engine becomes incredibly efficient. The intermediate pressure compressor in a Trent can hit 7,500 RPM compared to maybe 2,000 or 3,000 in a standard two-shaft design. This means it requires fewer compressor stages, literally fewer metal blades, to achieve the exact same pressure. The result is a shorter, lighter overall engine and a much higher overall pressure ratio, hitting up to 42-1 in the Trent 800. It's a real game changer. Let's move to our final section, the limits of fan size and the physical constraints of engineering. Now, what's really interesting here is tracking how fan diameter steadily grew across the Trent family. To push the bypass ratio higher and reduce fuel burn, engineers had to make the fans wider. The Trent 700 started at a very respectable 97.4 inches. But by the time we get to the Trent 900 for the massive Airbus A380, the fan is a staggering 116 inches across, pushing the bypass ratio to nearly 9-1. But, of course, there's a catch. You can't just keep making the fan infinitely larger. Why? Well, as fan diameter increases, the blade tip speed increases dangerously if the RPM isn't lowered. But slower RPMs mean you have to add more and more heavy turbine stages at the back of the engine just to extract enough turning power from the exhaust. Eventually, the crushing weight of those added turbines completely cancels out any fuel burn savings you got from the larger fan. Not to mention, more turbine disks heavily increase maintenance costs. Physics and economics eventually put their foot down. So as we rapidly approach the absolute physical limits of traditional rotating fans in terms of size and blade speed, it begs the question, will the future of high-speed flight rely on ramjets and scramjets? As we look towards supersonic and hypersonic horizons, we have to wonder what completely different engine architectures will power the next century of flight. Will rotating blades become a thing of the past? It's a fascinating question and something we'll definitely explore in a future explainer. Thanks for joining me on this deep dive into the engineering of the skies.